All right. Okay. So I got streaming turned on already. So let's go ahead and do a quick run about this test. All right.
You ain't tell us how bad we did already?
Well, I don't know whether it's bad or not. I mean, it's. I don't know. I mean.
Yeah, can we do this later when I wonder where
eventually prepared to it?
We can watch the video again.
Oh no, what?
Okay, so I'm going to open up, there are 3 versions of this test. So when you guys talk to each other after the test, there are actually 3 versions. So it may not be the same question. And then there are 3 more questions for 3 more versions for the Tuesday, Thursday class. So I have like 6 versions altogether. All right, so I'm just going to look at one first. And if you guys have any questions, just go ahead and stop me, and so we can talk about that. All right. Okay, so first question. So first question is about binary subtraction involving a 3-bit minuend and a 3-bit subtrahend. Step 1, is it possible for the overall borrow flag to be set and the sign flag to be cleared after the subtraction? Set means it is a 1, cleared means it is a 0. So in this case, I want the borrow flag to be a 1, and I want the sign flag to be a 0. So the question is, first of all, is it possible? If it is possible, then you go to step 2A, and you give me an example. That's all you need, is to show me that yes, it is possible. This is how we make it happen. If it is not possible, then you go to step 2B, and then you explain why it is not possible. Okay. So the first thing we want to do is to figure out, is it actually possible or not? Okay. So now the question is, how do we know whether it is possible or not? Okay, so what I'll do is I'm going to let you know, step by step, how I would approach this problem. There are many ways to do it. Some people can just do a trial by error, trial and error, and just kind of keep testing it until they're convinced that it's not going to work, or find a case where it starts to work. But there's a systematic way to do it. So basically, you want to ask the question, what is b of I plus 1, okay? Because this is in the notes, okay? So we know b of I plus 1, or in the notes it's called t because it's the borrow flag. Okay, how is it defined? Do you guys remember? It is the borrow between xi, yi, right? Or the borrow of qi and ti. I'm using the brackets instead of subscript because there's no way I can do subscript in a plain text editor. Okay, is that okay? And then the second question is, what is the sign bit? The sign bit is really just d of I. In other words, it is the most significant bit of the difference, of the result of the subtraction. That in return is basically the r of qi ti, okay, and then q itself is the exclusive OR between the x and the y. So when you look at this, it's not too difficult to set the borrow bit, because to set the borrow bit, you have to look at things from the signed perspective and just say that, okay, the unsigned perspective, whatever you're subtracting from has to be of a higher value from the subtrahend has to be bigger than the minuend in unsigned interpretation. There were several hands. Let me answer those questions. Yep.
Are you recording this?
Yes, I am. Second question.
Same question.
Oh, they're all the same questions. Are there any different questions? Okay, well, that's okay. Let me double check. Because sometimes yep, it is recording both the voice and it is streaming, so we're good. Okay. So you have to look at it, so the borrow flag is a 1, means the minuend is less than the subtrahend unsigned. Okay, so you have to look at it from the unsigned perspective. What about the sign flag? I want the sign flag to be a 0. So if the sign flag is a 0, it means, unless there's an overflow situation, it means the minuend is not less than the subtrahend, but in the signed interpretation. So the key here is to differentiate between unsigned versus signed. So you have to now give me a case where the subtrahend is less than the minuend when it is unsigned. The minuend is less than the subtrahend in the unsigned interpretation, but it is not less than in the signed interpretation. That is the key. Okay? So you have to cross the sign border, okay, in order for this to work. So let's see if this will work. So I'm going to try this one, okay? On the minuend portion, I'm going to try 0, 0, 1, okay? And on the subtrahend portion, I'm going to try 1, 1, 1. So you can see how 0, 0, 1 is representing the value of 1 regardless, okay? But 1, 1, 1, on the other hand, has two interpretations. Signed interpretation, it is -1. Unsigned interpretation, it is just 7. Okay, so let's carry out the subtraction and see what happens. So I'm going to do the full subtraction method and figure out the answer to this one. Okay, there we go. Okay, 1 minus 1 is a 0. 0 minus 0 is a 0. Neither gives me any borrow, so the borrow here is going to be a 0. 0 minus 1 is a 1. Whoops. Control Z, Control Z. So there's a 1 with a borrow, so this borrow is going to be set. 1 minus 0 is a 1. 0 minus 1 is a 1 with a borrow. This becomes the overall borrow of the subtraction. 1 minus 1 is a 0. So right here we have the case that I'm looking for, because the result is 0, 1, 0, which means the most significant bit is a 0. The sign bit is a 0. However, we also have the borrow bit being a 1, so it meets both requirements. So the correct answer is yes, it is possible, and I can use this particular example, for 2A. 0, 0, 0 itself will work as well, by the way, because 0, 0, 0 is representing the value of 0, which is less than the value of 7, which in the unsigned interpretation, but 0 is not less than -1 in the signed interpretation. So that works as well. I'm just using 1 instead of 0. Is that okay or not? No questions? All right, cool. So if there are no questions, I'm going to move on to the next question, number 2. Okay, so number 2 asks, let ki be the bit I of the carries, which is consistent with the note. Xi be the bit I of x, yi be bit I of y in the addition of x plus y. In class, we define x subscript I plus 1 to be blah blah blah, because there are 2 chances to have a carry to bit I plus 1. Consider changing the definition to exclusive OR, and I even define what exclusive OR, in the other way. Okay, so we have exclusive OR. So the question is the new definition going to work in an adder? And the answer is yes. Okay, so the answer is yes here. Okay, why is it yes? Okay, so the first thing we need to do is to figure out what is the actual difference between a OR versus an exclusive OR. All right, so we'll take a look at the truth table of those two. So we have x. Okay, maybe we shouldn't use x here. I'll use AB, okay? So we got A, we got B, and then we got the A plus B, or the A or B, and then we have the A exclusive of B. A exclusive or B. Okay, so we got 0, 0, 0, 1, 1, 0, and 1, 1. So we want to look at each one and say, okay, is the OR different from the exclusive OR? That's a 0, and that's a 0. Okay, no difference. This is a 1, This is also a 1, no difference. This is a 1, this is a 1, no difference. The last row is the only row that shows any difference. This is a 1, but this guy is a 0. So are we okay so far with this? I don't want to hear anything about tag, but you never talk about exclusive OR in class, because we did. And I also gave you guys the actual definition in the form that we talked about in class. Okay, so that part is not an issue. So now the question is, why would this last row not make any difference? So the answer is A and B cannot be true at the same time when we look at the carry circuitry in an adder. Why can't they be true at the same time? So here I gave you the equation. Okay, so xi, yi is one reason why we might have carry. Qi, ki is the other reason why we might have a carry. So now the question is, how come these two conjunctions cannot be true at the same time? Only up to 1 can be true at any time. That is the big argument, okay? Why? So to understand that part, we have to look into the definitions. So let me just repeat what I have in the previous slide so we can record it here. Okay, so ki plus 1 is known to be xi, okay, I'm just going to forget about the bracket. Okay, so it's xi, yi, or qi, ki, right? So, but now we have to look into what is qi. What do you think is qi?
Xi or yi.
Yep, it's xi exclusive or yi. Okay, so now we can argue, right? Because if xi, yi is a 1, under what situation is xi, yi a 1? When they're both 1s, right? Because xi, yi is the conjunction between xi and yi. So in order for that conjunction to be true, xi has to be a 1, yi has to be a 1. If xi is a 1, yi is a 1, what happens to the exclusive OR between those two? Becomes a 0. Okay? So you got 0 on one side of the conjunction, because this whole thing becomes a 0. So that means regardless of ki, the second conjunction cannot be true when xi is a 1 and yi is a 1. Is that okay? What about the opposite way? What about the case when this term is a 1? I mean, surely this term can be a 1. Absolutely. But it can only be a 1 if ki itself is a 1. I have no control over ki. All the earlier, less significant bits are contributing to ki. I have no control over that. So ki can be a 1 indeed. But if this term is a 1, what does it mean?
That means only xi or either xi or yi is, but not both at the same time.
It means they are different, right? As Boolean values, xi and yi are different. But there's only one way for Boolean values to be different. One is true, the other one has to be false, right? I don't even care which one is true and which one is false, because I just need to know that one is true and the other one is false. But if that is the case, what happens to the conjunction between those two? It has to be false. So that means if the first term, if xi, yi is true, the second term has to be false because the exclusive OR has to be false. If the second term is true, then the first term has to be false because xi, yi they have to be different. In other words, they cannot both be true. If they cannot both be true, that means this scenario would never happen with the exclusive OR. And if that scenario doesn't happen, then we only focus on the first 3 scenarios, in which case they are identical. So both OR or exclusive OR will work in that particular case. It doesn't mean that OR and exclusive OR are exactly the same in all cases, but in this particular case, they are interchangeable. Is that okay? So that would be the explanation that I'm expecting, for this particular answer. So the answer is, you have to use 2b. Excuse me. Oh, you have to answer with 2a because they are indeed the same, and then you just basically have to explain why only one side of the OR can be a 1. Up to one side can be a OR of the OR can be a 1. So you can use either or exclusive or, they both work. So the argument that I just made a little bit earlier is what I'm expecting in step 2A. You don't have to use exactly the same words, but you do have to refer to the QI, the definition of QI, and why that and how that relates to XI, YI. That is the key. Are we doing okay so far with number 2? Okay. Moving on to number 3. So number 3, in some versions, number 3 and number 1 are pretty much asking about the same thing. In the following space, show a binary subtraction of 3-bit numbers where the borrow bit is set, but the sign bit is cleared. Okay, in this case, it is the same. The subtraction should be carried in the longhand style, which means you have to carry out like the way that I did it in the in this particular one. So in question number 3, you have to do it like this. In question number 1, you do not have to do it like this. Okay, so you have to get all those rows. If you think this result combination is not possible, explain why it is not possible. But it is possible, you just have to show me that it is possible. Did anyone get a version that is not asking when the borrow flag is set and the sign flag is clear? No? I'm pretty sure that's a different version. Let me check. This is version 2. And let's magnify. Pretty sure there's a different version for number 3. Okay, so this version is borrow flag is set, sign bit is cleared. Okay, maybe I'm wrong. We'll check the third one. My computer is really slow, so bear with me here. Yep, same. Okay, so there's only one version of that question. That's okay. Question number 4. Question number 4 is pretty easy. I give you a base 5 number, and you have to tell me what is the base 10 representation of the value represented by this base 5 number. So in this particular version, the answer is, let me see, I think I can just insert it here. Do you want me to work on it here, or do you want me to work on it separately? Huh? Right here? Okay. So let's go ahead and insert equation. So what I'm looking for is, you just have to tell me what is the 3 representing. 3 of what? So, I guess that's not the right dot. C dot. Okay. So the 3 is multiplied to 5 to the power of what? 1. 1. And then we have to add 2 times 5 to the power of what? 0. And then I would do it this way. I would just be consistent and have the 0, even though it doesn't really contribute anything to the end, to the sum, I would still write it like this, because it is important to keep track of this is to the power of -1. Oops, I just put the wrong key. And then we have the last one, which is a 1 times 5 to the power of -1. Okay, so just giving me this much is going to get you some points already. Okay, you get at least partial credit for just doing this part. So then the next one is really just to carry out the multiplication. 5 to the power of 1 is just 5. 3 times 5 is 15. 5 to the power of 0 is 1. 2 times 1 is 2. The 0 is just a 0, so it doesn't contribute anything to the sum. And then 5 to the power of -2, okay, I wrote it incorrectly here, is 0.04.
Yeah.
So this is just adding, oops, 0.04. There we go. So after you add up all of these terms, then in this particular case, we get 17.04 as a base 10 number. So yours would be slightly different. You know, the digits are different, but the format should still be the same. You tell me that it is the quantity times some power of 5. I'll be looking at the pattern. 5 to the power of 1, 0, -1, and -2. The term that has a 0 multiplier, you can miss that one. I'm not going to take any points off. But all of the other ones, you have to explain to me, you know, 3 of what, 2 of what, and so on. And then you add all the sum together, and the final answer, they're all worth points. But I would say most of the points goes to the first step. Is that okay? All right. The next one is kind of like a reverse. We have a base 10 representation. In this case, it's 10.375. And I have a typo in the following space. And this is another typo, it's derive, not drive. Derive the base 2 representation of the value step by step. Okay, so how should we do this? 10.375 is, I want you to express it as a sum of base 2, powers of 2. So in this case, it is 8 plus 2 plus a quarter, and then plus an eighth. Okay? And then you look at the 8 as 2 to the power of 3, and then the 2 is 2 to the power of 1. The quarter is 2 to the power of -2, and then the eighth is 2 to the power of -3. Okay? Then you have to kind of fill in the missing terms, or if you prefer, you can do it this way too. You can say this is 1, 0, 0, 0 in base 2, plus 1, 0 in base 2, plus 0.01 in base 2, plus 0.001 in base 2. In other words, we are just turning the powers of 2 into binary numbers, simple ones. And then once you get to this point, you can say this is now 1010.011 in base 2. So that's one way to express it. I mean, if you guys have a different way to complete the conversion, that's fine too, as long as it is step by step and I can see how you do it. Okay? You can also do it using the method of digit by digit, because I gave you a universal equation in my notes. So you can apply that equation as well and just say that, okay, the first digit is this, the second digit is this, and so on and so forth. That works as well. Yep.
I forgot the decimal point in the binary number. Didn't take points.
Yeah, that's kind of important. It will turn that particular line item in my rubrics from an A to a B. So it's not going to be. So you'll lose a little bit of points, but it's not going to be that much. All right. Are there any questions about number 5? No questions. Moving on to number 6. Okay, number 6. Assume we can use gates of any number of inputs, and assume all gates have the same propagational delay or latency. If we know that the 3-bit carry look ahead adder takes 3 nanoseconds to finish computing the sum and the overall carry bit, how long does it take for a 6-bit carry look ahead adder to complete its computation? Explain your answer. So first of all, the answer itself is going to be 3 nanoseconds, same, because that is the whole point of carry look ahead. Is there's no carry propagation. It doesn't matter how many bits you're adding, it is still going to take the same level of gates. Okay, so you have to explain that here. So you basically say, carry look ahead means the level of gates for computing each carry bit is the same. Therefore, the overall amount of time to compute the sum and the overall carry remains the same regardless of the number of bits to compute. That would be the answer. Because the whole point of carry look ahead is so that we can speed up the whole process. Is that okay or not? All right. We're down to the last question. Number 7. After a binary subtraction, we know, oh, I like this one. I love this particular question. We know the following condition is not possible. In other words, don't even bother to think of a way to generate it. I'm telling you it is not possible, okay? Explain why it is not possible, why it is the case, using the definitions of the borrow bits, difference, and overflow bits. In other words, go back to the definitions because that is what's going to help you. Hint, a state combination of 2 of the flags implies the value of the third flag that contradicts the given condition. So, if you use, and I give you the order here, think of the definition of the overflow flag, the sign flag, and the borrow flag. Okay, so I chose that order for a particular reason. I should have used a B in the middle, then it becomes OBS, right? That we have used. But I specifically use OSB for a reason. All right, so we'll basically take a look at the overflow flag first. What is the definition of the overflow flag? You can look at your notes, right? Because this part is definitely in your notes. Okay, so can someone tell me, let's use M as the sign bit of the minuend, S as the sign bit of the, that won't work too well, would it? Yeah, I suppose it's still okay, lowercase then. Okay, so it's M, not S, not D, okay? S is the most significant bit of the subtrahend in this case, and then the OR is not M, S, D. Do you guys remember this? Is it vaguely familiar? Okay. So I'm telling you, in this combination, in this impossible combination, I'm saying that overflow is a 1. What is that telling you? It's telling you that the OR, the disjunction, is giving you a 1, right? Okay. And then I put a sign here, okay? The sign flag is the second one. So the sign flag is the sign of the difference, right? So which one of these conjunctions has a chance of becoming a 1 if D in this case, because remember sign is the most significant bit of the difference. Which one, the first one to the left hand side or the right hand side, which one has a chance to become a 1 when the most significant bit of this difference is a 1?
Right.
Nope, second one. Because remember, D in this lowercase d is our sign flag. It is the most significant bit of the difference. This one has a negation, so that means if D is a 1, the negation is a 0, but since it's in a conjunction, so the whole conjunction is going to be a 0. On the other side, D is a 1, and it has a chance, the entire conjunction has a chance of becoming a 1. Is that okay? Yes? Okay. So O is 1 and the sign is a 1 implies not M S D is true. Can we buy this? The other one has no chance of becoming true. This one has a chance. Okay? All right, so if that is true, what is it telling me? It's telling me that the most significant bit of the minuend is a 0, right? Because not M has to be a 1. If not M is a 1, then M is a 0. Does that make sense? Making any sense? Okay. Okay. So it is also telling us the most significant bit of the subtrahend is a 1, because that's what this lowercase s is. Is that okay? Okay, so once we know this, why is that important? What is the borrow bit? The overall borrow bit is what? it's just like all the other borrow bits. There are two ways to set the borrow bit, right? So the first way to set the borrow bit is basically in this particular notation, it is the same thing as not ms. And then the second way to set the borrow flag is not q t of that particular bit. But we already know that the most significant bit of the minuend is a 0, so not m is a 1. We also know that the most significant bit of the subtrahend is a 1, so lowercase s is a 1. We got a 1 already, so the borrow flag has to be set. But in the combination, I'm telling you that it is a 0. So now we have a contradiction. It is not possible. The borrow flag cannot be a 0. But did you see how I just used the definitions of the terms to help me with this? And in the specific order of the overflow flag and the sign flag, and then the result is we can deduce the borrow flag has to be a 1, but it is given to be a 0. So now we have a contradiction. It is not possible. Is that okay or not? So out of the 7 questions, how many, which one do you think is the hardest? They're all equally hard. Yep.
The latency one.
The latency one? That one, when I wrote that question, I was, expecting that one to be kind of like an easy one. Because because that's the whole point of carry look ahead. Is like we don't want propagation. We don't want the carry ripple method, where the longer the addition, the more weight you have to the more you have to wait for the last carry to become effective. That's the whole point of carry look ahead. And we kind of look at the hierarchy of the gates also in class when we analyze the actual latency. So I was hoping that that would give you an idea of how to analyze that one. Yep.
I think I struggled with number 1 because I didn't realize if it was signed or unsigned it was referring to, and so it kind of threw my head off of what I was looking for when I was thinking about it.
Okay. So number 1 and number 3 are basically the same kind of question.
And I wasn't sure where I was at exactly.
Yeah, because the borrow flag, if you want to understand it intuitively, is for unsigned interpretation. The subtrahend is greater than the minuend, so you owe something. Borrow means you're owing. But the sign flag is for signed comparison. Basically after the subtraction, you have a negative value. So in that particular question, it's asking you to come up with a bit pattern that can be interpreted differently, whether it is signed versus unsigned. So that points you directly to the negative values, because the positive values are the same. So in the case of a 3-bit number, 0, 1, 2, 3 are the same whether it is unsigned or signed interpretation. But the other 4 values can be either positive or negative, so you have to focus on those. Any other question that you think was kind of challenging? Not challenging?
1 and 3, 7 was a tricky one because I was.
Yeah, that's why I put it into as question number 7, just in case people run out of time. This is one of those questions that people can kind of like miss because it's not. If I put this question first, then people would be spending more time on the question that is worth the same amount of points as all of the other questions. So that's why I put this as the last question. It's like, yeah, if you guys can get to that one, work on it. But if you run out of time, work on the other ones first, because the other ones are supposed to be easier. So now that you guys know the answers, how did you do?
Terrible.
1 and 3 cut me. 1 and 3 got me.
1 and 3. Well, that's 2 out of 7. Not too bad.
Not too bad.
Not too bad. I mean, okay, so remember the scaling of this class. 37.5% is a C. So if you miss 2 out of 7, you probably still get a B or close to a B, assuming you get the other 5, right? So keep that in mind, okay? It's in the syllabus, okay? How I assign letter grades based on the percentage is in the syllabus, so you might want to read that again. This is 20% of your final grade. Homework, all the lab activity adds up to another 20%. The next midterm, exam 2, is another 20%, and then the final exam itself is 40%, okay? But what is not going to change with the other exams is what kind of question I'm going to ask you. Okay, it will still be the kind of questions like these ones, which will basically test your understanding of the material and also whether you can apply your understanding, at the time of the exam. So I think that was the part that some people might not have expected. Have you guys ever taken an IQ test?
Nope.
No? Okay. So in IQ tests, they would tell you something like this, like Tom likes to go on a trip with so and so. That person likes to go on a trip with these people. This people doesn't like those people, and so on and so forth. So you ask okay, how should we arrange the seating arrangement so that people that hate each other would not be in the same car, that sort of thing. That's what this is boiling down to, really. Except it's not as much fun.
What'd you get, like 170?
No, I think I got 140 or something like that.
That's what I got.
But IQ tests are not indicative of intelligence, okay? Because it's really testing a very, very specific way of thinking. I mean, so that's not.
Nothing. You can't measure intelligence using a linear vector. It's too simple.
Okay. So are there any questions?
It's true though.
Now the one thing that I can tell you is if the whole class, like totally bombed out, like the best score is 4 out of 7, I'd usually recurve the whole thing. I would ignore, I can choose how many questions that I can throw out. Like, I can throw out the one question that has the lowest score, 2 questions, the lowest scoring 2 questions, and so on. Typically, I throw away 1 when there's a need. Very seldom do I need to have like 2 thrown out. That would be kind of exceptional. Yep.
Wait, so you're saying you throw away the 2 lowest questions, but what if that was like your best question?
No, the 2 lowest scoring questions. The 2 lowest scoring questions. Okay, so give you a solid example. So let's say you get full score for 5 questions, okay, and have 50% for the other 2 questions, for the last 2 questions. So the last 2 questions will be thrown away. So that means you end up with quote unquote a perfect score.
Right. Okay.
So nobody's going to lose in this scenario.
He's not talking about a class-wide.
Yeah.
thing.
But it's not the fixed 2 questions. Everybody can be different.
Yeah.
If you did not answer the first question at all, and you did not answer the number 7 at all, then I'm going to throw a number 1 for you, and I'm going to throw a number 7 for you. So it's quote unquote fair, from that perspective.
So when you usually do something like that, is that after looking at both classes that you teach, or just like individual classes?
Individual class, but since the questions are very, very similar, I'm expecting the distribution to be about the same for both classes. If one class is significantly different from the other one, I'm going to be looking for answers. Typically, okay, so this is a tip, but you guys know that already. In a test, especially something like this, if the distribution is bimodal, like either people answer with very low score, and then there's a whole bunch of people with very similar scores, it typically means the answer key is available and somebody had a copy of that and distributed to students. That cannot possibly happen in this class because I don't have the answer key either. I was working on the problems as we speak. So there's no answer key whatsoever. So I'm expecting a bell curve of some kind in this class.
Has the other section taken the test yet?
They took the test last Thursday,
Oh,
but I haven't talked about the answer.
Okay, gotcha. Right.
When I made the question, I was fairly sure about the answers, but I didn't write down anything. So nobody has a key. I don't have a key either. Any other questions?
Did you test your other class on floating point?
No, the other class is the same as this one.
Oh, I thought we were behind by 2 months.
Yes, we are sort of behind, but I decided not to quiz them on the floating point either, because they're still working on the floating point number assignment, just like you guys are. All right. So are there any questions? Nobody is asking, like, you know, how many percent do I need to get a B? 62.5. Yep. Mm-hmm. Does anyone want to know how many percent you need to get an A?
Sure, I don't remember.
87.5. Yep.
So basically, I got
See how they're all multiples of powers of 2?
Oh.
And you guys
Thanks,
are,
two.
no more powers of 2, please. Make it go away.
And the test grade will be uploaded within like a week or something like that?
The grade itself? Well, okay, this is what's going to happen, clerically speaking. I'm going to take the big pile of paper home. I'll de-staple every single one, run them through my scanner, and then save the file for each person individually, upload everything to my Google Drive, come up with the grading rubric, and then I'll start grading.
Gotcha. Okay.
So it's going to take a little bit of time because of all the clerical stuff that has to
Right,
happen.
right, that makes sense.
Yep.
So we have the assignment due Wednesday. Is that after the lab?
That's during the lab itself.
What's due during the lab?
It's due during the lab, I think on Wednesday.
I have a question on what exactly.
Into the little section in
Yep.
the lab? Okay.
Yep.
What exactly are we supposed to have for us? Like just a line of code there's a series of lines of code that makes the mantissa go to maximum bits and then base 2.
Correct. So to do the homework assignment, you're expected to write the code in the project itself. So in code blocks, you're supposed to fill in the content of the function that we are working on. And then you feed the number that you're supposed to work on into the program. And then you set up a breakpoint in main at the very last moment, and you capture whatever those numbers are in n, which is a struct number, and then you copy and paste it into Canvas, and that's how you turn it in.
Okay, so we're just pasting the result.
Correct.
Got it. That sounds
Yep.
good stuff.
But you are supposed to work on the code, the actual code, to get to the answer.
Well, I don't know how to get the answer without the code, so I couldn't do the math by hand.
That's the whole point.
That wasn't gonna happen.
Yep, that's the
code
whole
had to
point.
work
Is
first.
most calculators cannot work without those numbers either. All right, so is that clear? What you guys have to do for the homework assignment?
We're not turning in any code at all.
You're not turning in the code. You're turning in the results of rendering. Yep. But anyone who's taking a shortcut out of this one is it's gonna suck big time in exam 2, because in exam 2, I'm gonna ask you guys. I will have questions to see if you guys understand the process of converting a base 10 scientific notation to a base 2 scientific notation. Not having written the code is not gonna help. So the homework is only worth this much point. The test, a lot more. So I think you guys can do that. Cool. Okay, so I'm done with the review of the test. If you guys don't have any further questions, yep.
Just one more question.
It's the hardest part
Okay,
is
I
figuring
can
out
turn off the
here.
recorder.
Okay.
Yeah.
Well, you gotta